It's funny. We all just carry around these supercomputers in our pockets these days.
Oh, yeah,
And
absolutely.
we expect absolute magic from them every single second.
Right, like instant gratification.
Exactly. You tap a button to execute a trade or pull up this massive data set on your phone, and the response is, well, it's basically instantaneous.
Millisecond.
Yeah, milliseconds. But behind that single tap of glass is this, it's an invisible, flawlessly orchestrated chaos.
Oh, it really is.
A load balancer hits a spine leaf fabric, it finds the exact top of rack switch, routes down into a specific hypervisor's virtual switch, and then hits a single VM.
And it has to do all of that within, like, really strict microsecond latency budgets.
Right.
We were talking about highly distributed multi-tenant architectures where, millions of packets are constantly being encapsulated, routed, and decapsulated.
Wow.
And we've normalized it completely, but from an engineering perspective, keeping that infrastructure running without catastrophic collisions is basically a daily miracle.
It really is a massive physical undertaking. And
Yeah.
the question that always gets me is, how does this architecture actually get managed at scale?
Yeah, that's the big one.
Because as density increases, the complexity of managing the physical and virtual networks routing that data, it just goes up exponentially.
Oh, totally.
How do you prevent human error from bringing the whole house of cards crashing down when you are operating at that kind of velocity?
Well, that is the defining engineering challenge for enterprise IT right now. I mean, the industry has reached a tipping point where you simply cannot rely on manual per-device configuration anymore.
Right.
The bandwidth demands are just too high, and the blast radius of a single misconfiguration is way too wide.
Okay, let's unpack this because we have a deep dive today that tackles exactly that challenge.
Yeah, this is a great one.
We're looking at a really fascinating breakdown by Kevin Kolb from Supermicro, and it details how their platform, Super Cloud Composer, or SCC, provides this unified solution for orchestrating this exact kind of enterprise network infrastructure. Our mission today is to trace this whole life cycle. We're going from the high-level switch architectures and multi-vendor integrations all the way down to the granular mechanics of, provisioning VLANs.
That's fun stuff.
Right up to the exact moment a network administrator hands off that network to the server architect.
It's a really critical workflow to dissect.
Yeah.
And while we are going to get into the specific routing technicalities,
Right.
this is fundamentally a story about operational velocity.
Absolutely.
It's about leveraging abstraction layers to bridge this massive gap that has, traditionally siloed network operations from server operations.
So let's start in the master control room. We're looking at SuperCloud Composer, which is positioned for the lifecycle management of these high-performance network switches.
Right.
But here's where it gets really interesting. It's not just an ecosystem play for Supermicro hardware.
No, not at all.
This platform provides a unified dashboard experience for major third-party technology partners as well. We're talking about orchestrating switches from Juniper, Arista, and Mellanox, all from the exact same interface.
What's fascinating here is the heavy reliance on the phrase open distributed infrastructure management.
Yeah, that stood out to me too.
Because historically, enterprise data centers have been totally crippled by vendor lock-in.
Oh, completely.
If you build a fabric on Juniper, your network engineers have to be fluent in Junos OS.
Right.
If you pivot to Arista, they have to master EOS. You essentially end up with these incredibly rigid CLI fiefdoms inside your own data center.
It's a massive operational bottleneck. You have engineers spending half their time translating the intent of a network change into the specific proprietary syntax of whatever logo happens to be stamped on the metal bezel of that switch.
Exactly. And SEC sidesteps this by heavily leaning into the industry's standardization on SONiC-based switches.
Okay.
Because SONiC, which is software for open networking in the cloud, utilizes the switch abstraction interface, or SAI.
Right.
And that completely decouples the network operating system from the underlying ASICs.
Oh, wow.
So SCC sits above all of that, utilizing RESTful APIs to push configurations globally. It doesn't really matter if the silicon underneath is Broadcom or Mellanox.
I love visualizing this. Managing a legacy enterprise network is like being an old-timey telephone operator,
Yeah.
Frantically plugging cables into specific proprietary switchboards just to keep the lights on.
Totally.
SCC functions more like a a modern digital air traffic control tower.
That's a good way to put it.
The system and the admins running it, they don't care if the planes on the runway were manufactured by Boeing, Airbus, or Lockheed.
Right.
They just need radar visibility on all of them simultaneously to manage the traffic flow via a standardized protocol.
And we really need to emphasize the sheer speed of the planes we were talking about in this scenario.
Oh yeah, the bandwidth is insane.
The documentation notes that this management layer is orchestrating hardware supporting speeds ranging from 1G and 10G access ports, all the way up through 25G, 40G, 50G, 100G.
Wow.
And it culminates in 400G backbone links, utilizing that sonic-based NOS.
Pushing 400 gigabits per second through a single piece of silicon is just staggering.
It fundamentally changes the physics of the data center.
Yeah.
When you were operating 400G optics, you were dealing with PAM4 modulation, massive heat dissipation challenges, and incredibly complex ASIC forwarding tables operating at line rate.
Right, it's not just plugging in an Ethernet cable anymore.
Exactly. You cannot have humans manually typing out CLI commands to manage traffic flows of that magnitude.
No.
One transposed digit in a subnet mask or a VLAN tag, and you haven't just dropped a connection, you've severed a primary data artery.
Oh, man.
And you've potentially triggered a routing loop that could take down the entire fabric in milliseconds.
Which perfectly sets up the engineering challenge. We have this universal remote control SEC, and we have the massive 400G hardware it supports. But to actually prove out the orchestration capabilities, the Supermicro team didn't just talk theory. They built out a physical sandbox from scratch to demonstrate the provisioning.
They needed to build a highly realistic, virtualized compute environment to put the network abstraction to the test.
Right. And because this sandbox is designed to handle heavy interconnected VM traffic, the architects had to lock in their hypervisor and backend storage choices immediately.
Yeah.
They looked at Proxmox, VMware, Verge.io, and Hyper-V.
Yep.
But ultimately, they chose to deploy a KVM hypervisor utilizing CentOS as the bedrock for the compute layer.
It's a highly pragmatic choice for this kind of infrastructure validation.
Yeah.
Yeah, because KVM on CentOS gives you incredibly low virtualization overhead, direct access to the Linux kernel's networking stack.
Right.
And it's a standard battle-tested environment for proving out complex network topologies without introducing, proprietary hypervisor quirks into the mix.
But then we get to the storage backend, and I have to pause here.
Okay.
Because to host the virtual machine data stores, they went with a network file system, or NFS.
Right.
And the rationale provided is that NFS is, quote, inexpensive and easy to implement. Wait, hold on. If we're talking about massive enterprise scale, utilizing platforms that support 400G fabrics, NFS seems incredibly basic.
I can see why you think that.
It almost sounds like cutting corners for a demo rather than deploying a true enterprise-grade block storage solution or an NVMe over Fabric setup. Why default to inexpensive and easy?
Well, it looks like cutting corners until you realize what variables they're actually trying to isolate in the sandbox.
Okay, what do I mean?
The core of this demonstration isn't about maximizing storage IOPS or testing the latency of NVMe storage controllers.
Right.
They are testing the network provisioning, the routing, and the resilience of the switch fabric itself.
Okay, so they don't care about the quality of the water tank. They just need a reliable reservoir to prove the plumbing can handle the pressure without leaking.
Precisely. NFS serves as a highly stable, completely transparent anchor point.
Ah, I see.
If a packet drops or a path fails, they know instantly it was a switch misconfiguration, not some obscure multipathing error within a proprietary ZAN protocol.
That makes a lot of sense.
And if we connect this to the bigger picture, to thoroughly test that plumbing, the network design relies heavily on Link Aggregation Control Protocol, or LACP,
Right.
to connect the compute layer to that NFS data store.
Right, port bonding. The architecture diagrams show two 1G NIC interfaces bonded together to move the data store traffic using a specific PVID VLAN.
Yeah.
And then the compute traffic gets a dedicated 10G interface.
But we need to be clear about what LACP is actually doing under the hood.
Okay.
Because it's not just splicing two cables together to make a thicker pipe.
Right, smarter than that.
Exactly. LACP operates at the data link layer to bundle physical links into a single logical channel. But the real magic is in the hashing algorithm.
How so?
Well, if you just randomly sprayed packets across two different physical cables, packets belonging to the same TCP stream could arrive out of order.
Oh, and that would force the receiving server to reassemble them.
Right, which completely destroys your CPU performance.
Yeah, that makes sense.
Instead, LACP uses a hashing policy, usually looking at the source and destination MAC addresses, or even the IP and TCP ports, to ensure that all packets for a specific conversation always travel down the exact same physical wire.
Oh, wow. So it's load balancing the conversations, not the individual packets.
Exactly. It distributes the total bandwidth load across the aggregate link while maintaining packet order.
That's brilliant.
And simultaneously, it's constantly exchanging LACPDUs, these data units, between the switch and the server.
Okay.
If one of those 1G cables is physically severed or a transceiver dies, the switch stops receiving those LACPDUs on that specific port and instantly pulls it from the hash table.
Wait, instantly.
Instantly. The server's hypervisor doesn't even know the link died. The traffic just seamlessly continues on the surviving port.
That is hardware-level fault tolerance reacting in milliseconds.
Exactly.
And they note that while they're using 1G and 10G links for this specific sandbox, in a production enterprise environment, these LACP bundles would easily be scaling to 100G, 400G, or even theoretical 800G aggregations as that hardware hits the market.
The underlying math and the protocols remain the same, whether you are pushing 1 gigabit or 800 gigabits.
Right.
The challenge is purely in how you orchestrate it.
Which brings us to the actual provisioning. The architectural blueprint is locked. We have KVM on CentOS connecting to the NFS storage server via these LACP bonded links, all converging on a top-of-rack switch.
Right.
Now we have to translate that blueprint into the actual switch software.
This is where we transition from the theoretical design to the operational reality.
Yeah.
And frankly, this is where the traditional CLI approach falls apart under its own weight.
Right, because the presentation transitions to SCCL's network provisioning wizard, and we watch them configure a third-party Arista switch directly from the Supermicro dashboard. The first technical hurdle is carving up the logical networks, creating the VLAN list.
Yes.
They configure VLAN 100, 200, and 300 specifically for compute traffic, and they tag them. Meanwhile, VLAN 1 is set as the native VLAN.
This brings us right into the mechanics of 802.1q trunking.
Okay.
When we are passing multiple distinct networks over a single physical cable, we rely heavily on frame tagging.
So what does this all mean mechanically? I mean, think of 802.1q trunking like an automated high-speed shipping yard.
Okay, I like that.
The native VLAN, VLAN 1 in this case, is just loose cargo rolling on the dock. It's untagged.
Right.
But the tagged VLANs are compute traffic. The switch is literally injecting a 4-byte header, like a strict shipping container manifest, directly into the Ethernet frame.
Yes. Specifically, it inserts a tag protocol identifier and a tag control information field right after the source MAC address.
And the receiving switch, as ZSIC, has to read that 4-byte manifest at line rate, route that container to the exact correct logical lane, say VLAN 200,
Right.
and then it strips that header completely off before it hands the packet down to the server, so the server never even knows it was multiplexed.
That is a phenomenal way to visualize it. It requires immense processing power at the ASIC level to inject and strip those tags at 400G speeds.
I can't even imagine.
So in the SEC wizard, the administrator maps these VLANs to the primary uplink port, which is Ethernet 11.
Okay.
This port is the lifeline connecting the top-of-rack switch to a corporate layer 3 switch, providing the external routing needed for the servers to pull down OS mirrors and software updates.
So the admin just clicks Ethernet 11 in the GI, assigns VLAN 1 as native, drops 100, 200, and 300 as tagged, and hits apply.
Yep, that's it.
But the real showstopper of the demonstration happens right after this, when they move to bulk provisioning.
Oh yeah, the bulk port configuration. This is the operational payoff.
They need a whole block of ports to act as trunk ports for the incoming compute servers, specifically ports 15 through 37.
Right.
In the SCC interface, they literally just highlight that entire block of 22 ports and, with a single action, convert them all from standard access ports into 802.1q trunk ports with all the correct VLAN tags applied.
We really have to contrast this with the traditional operational reality.
Let's do it.
If a network engineer had to provision ports 15 through 37 via a command line interface on that Arista switch, it is a painstakingly manual loop.
Oh man, I remember those days.
Right. Log in. Enter Global Configuration Mode. Select Interface Ethernet 15. Type the command to set switch port mode to trunk. Type the command to allow VLANs 100, 200, 300. Exit. Select Interface Ethernet 16. Do it again.
It's awful.
You are relying on a human to type identical strings of syntax dozens of times flawlessly.
It's as the definition of busy work. And the fatigue leads directly to errors.
It leads to catastrophic silent failures.
Yeah.
What happens when the engineers on port 28, they get distracted and they accidentally type allow VLAN 10 instead of VLAN 100?
A shipping container manifest gets stamped with the wrong destination.
Exactly. So the server gets physically plugged into port 28, the link light turns green, the hypervisor boots up.
Everything looks fine.
Everything looks totally healthy at layer 1 and layer 2,
Yeah.
but the server can't reach the NFS data store, and it can't reach the internet because it's logically trapped on a non-existent VLAN.
Oh, that is a nightmare to troubleshoot.
Troubleshooting that requires an engineer to manually audit the running configuration of the switch line by line to find the single missing zero.
By using SCC to abstract that process into a visual bulk provisioning API call, you completely eliminate the variable of repetitive human keystroke errors.
Completely.
The network is wired, the LACP bonds are hashing correctly, the 802.1q tags are mapped. The traffic is ready. Which brings us to the ultimate purpose of this rapid provisioning, which is the handoff.
Right, because the network engineer isn't actually consuming this infrastructure, they are providing it.
The immediate result of pushing that configuration via SCC is that the network admin can instantly hand a fully verified fabric over to the server architects. The server team can then step in, deploy the VMs on KVM, establish their internal virtual bridges within CentOS, and basically just begin testing application reachability.
This raises an important question about the evolution of IT workflows.
What's that?
For decades, the network operations team, NetOps, has been an inadvertent bottleneck.
Yeah, that's definitely the stereotype.
And not for lack of effort, but because manually configuring and auditing CLI deployments on proprietary hardware, it just takes time.
It takes forever.
It forces a really rigid ticketing system. ServerOps says, hey, we need 20 new hypervisors spun up.
Right.
NetOps says, okay, submit a ticket, we'll audit the switch capacity, write the CLI scripts, schedule a maintenance window, and we'll get back to you next week.
The classic silo delay. But SCC Era's abstraction layer completely changes that dynamic. And the presentation points exactly to where this is heading next.
Oh yeah, the automation piece.
It's not just about a human clicking a bulk provisioning button in a web GUI. SCC exposes all of this functionality via a northbound REST API.
This is the critical leap. By exposing the infrastructure as an API endpoint, it allows for complete programmatic control using tools like Python and Ansible.
So rather than a network admin clicking through the SCC dashboard, they are writing an Ansible playbook.
Yes. And the beauty of Ansible interacting with a REST API is idempotency.
Okay. Expand on that for a second.
Sure. So a network engineer writes a declarative YAML file that basically states ports 15 through 37 on these 10 switches must be trunk ports allowing these specific VLANs.
Okay.
Ansible hits the SCC API. If the ports are already configured correctly, SCC does nothing.
Nice.
But if they aren't, it changes them to match the file.
So it ensures the physical infrastructure always perfectly matches the code repository.
Exactly. The network administrator is no longer a manual typist of switch syntax.
Right.
They evolve into a net DevOps engineer. They are managing infrastructure as code.
Which is huge.
It allows IT shops, especially smaller enterprises where, one senior engineer might be wearing both the NetOps and ServerOps hats, to deploy complete multi-rack environments in minutes rather than weeks.
Why should anyone listening right now, maybe someone who isn't racking switches every day, care about this IT handoff?
That's a good question.
Because this invisible relay race is what determines whether the new app your company launches takes 3 months to deploy or 3 days.
Exactly. It tears down the operational silos entirely and just speeds up the whole business.
So let's take a step back and distill this architecture we've just explored.
Let's do it.
We started with the macro view. SuperCloud Composer acting as this universal translator, standardizing the management of Supermicro, Juniper, and Arista hardware via SONiC and APIs, entirely sidestepping that horrible vendor lock-in.
And from there, we dug into the physical sandbox mechanics.
Right.
Analyzing how LACP hashing provides transparent fault tolerance for those critical NFS storage links, while the 802.1q trunking handles the logical isolation of compute traffic via line rate ASIC tag injection.
And then we saw how abstracting those mechanics into bulk API calls eliminates the catastrophic risks of manual CLI configuration, turning a massive provisioning bottleneck into just an instant automated handoff to the server architects.
It is a really compelling look at the maturity of infrastructure orchestration.
Yeah.
I mean, we are finally moving past the era of artisanal, handcrafted network configurations.
We really are. But before we wrap up, I want to pull on one specific thread that this naturally leads to.
Okay, ready.
We've talked heavily about REST APIs, Python, and Ansible playbooks driving this automation, alongside hardware capable of 400G and eventually 800G line rates.
Oh, yeah.
If a platform like SEC has successfully abstracted the entire life cycle of a switch, turning physical port configuration, VLAN tagging, and LACP bonding into simple API endpoints,
Yeah.
what happens to the role of the traditional network administrator when we inevitably connect those RESTful APIs to autonomous predictive systems?
Oh, man, that is the ultimate destination for this technology.
Because right now, we still have a human writing the Ansible playbook. We still have a human defining the YAML file. But as the infrastructure becomes pure code, are we rapidly approaching a threshold where the hypervisors and applications themselves monitor their own utilization? And when they detect a bandwidth spike, they simply negotiate and provision their own switch fabric via the SEC API?
The application layer directly programming the network layer in real time, with zero human intervention.
Exactly. No engineer drawing an architectural diagram. No one scheduling a maintenance window.
Just autonomous scaling.
Just the servers dynamically spinning up 400G LACP bundles, carving out new VLANs, and tearing them down the millisecond the compute demand drops.
That is wild to think about.
It turns the static data center into a living, elastic organism. Just something to ponder the next time you seamlessly connect to a cloud application and expect an instant response, completely oblivious to the invisible, automated choreography executing in the dark.